All right, kids, so let's talk about solubility curves. So solubility curves describe a solution in three ways. It can be unsaturated. An unsaturated solution means that the solvent or water can still dissolve more of the solute or the solid. A saturated solution means the solvent or water has as much solute or solid as it can hold. And then there's also a situation of supersaturated, which we'll talk about in a minute. So let's take a look here at our FET, which you really should have done. So here's water, and here's our solutes. That's our solvent. Here's our solute, and we'll put the concentration meter in there. Drink mix is our solute, and we're going to put that solid in there. And as you can see, it's increasing in concentration, but it can still hold more. So right now, we would say this is an unsaturated solution. It can still hold more solid. So it's not very saturated, but as it gets darker, as we dissolve more and more solid, it gets to a point where it can't hold anymore. And that is called saturation. And I'm almost there here. I think I'm almost there. There it is. So as you can see these little dots here, any bit of solid I throw in there is not even going into the water anymore. It's just going right to the bottom because it's saturated. The water can't hold anymore. So our unsaturated solution is the water or solvent can still hold more of that solute, which is a situation before that right here, right? This is unsaturated solution, but it gets to a point where it's saturated, where it can't take anymore. And even if I want to add as much of this, hold on a second, we're not there yet. So this is unsaturated, 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 and then it's going to become saturated. And then it doesn't matter. Look here, the concentration doesn't change even if I add more solid. And that's because it's saturated. And it can't take anymore. Now, there is on occasion something called supersaturated. A solution can be supersaturated where you go beyond the saturation point and you can put an extra solute in there, and we can talk about how that's possible here in a minute. So let's take a look at these solubility curves. Solubility curves will have temperature on the x-axis, solubility on the y-axis. Generally, the solids are more soluble in water at high temperatures, and the gases are more soluble in water at low temperatures. We'll talk about why in a second. But let's take a look here at the charts. So these are ionic solids dissolved in water. And as you can see, the temperature is down here, the solubility is on this side, and the solubility is increasing as the temperature increases for all these solids. All right. Whereas for gases, here's methane and oxygen and carbon monoxide and helium, they decrease in solubility as you increase your temperature. You're getting less and less of it to stay in the water. And why is that? Well, let's take a look here. If I draw a little beaker, let's draw a little beaker. I don't like that color. Let's draw a black beaker. So here's a beaker. Oops. Ugh, that's hideous. All right, let's do it over here. Here is a all right, there's a beaker. It would never stay on a table, but it's a beaker. All right. And then in this beaker, I'm going to draw a whole bunch of water. So here's some water, solvent particles, molecules as it were. So here's a whole bunch of solvent in that beaker. And then I'm going to draw some solute. And I'm going to make the solute red. Here we go. And we'll draw some solute particles here, molecules or whatever you have. So this is dissolved in my solvent. So if these were gas, if these little red things here are gas, and you know this from soda, right? If you pour soda in glass, what happens? The gas sort of bubbles out and wants to leave, right? Well, what would happen if you heated up that liquid? You're going to give more energy to those bubbles. So those bubbles are going to want to leave even faster. So that is why, if you think about it, this bubble's already on the surface. It's going to fly off. This bubble here is close to the surface. You give it some energy, it's going to fly off. And so we will have a lower, oops, here we are. As we increase our temperature, we're going to have lower and lower solubility. It's not going to be able to hold as much of these gases because the gases are going to want to jump out. Likewise not likewise, but similarly with ionic solids, if you really think about what's happening here, to dissolve an ionic solid, water needs to pull apart its, right? So here's an ionic solid, and water needs to pull this apart. If you heat it up, you're giving the water more energy to pull harder on these things to separate them. So if they were sort of being persnickety about getting, they want to stay together, they don't want to come apart, you give the water more energy by heating it up, you're going to be able to pull these apart better. So increasing energy, increasing temperature will increase typically your solids uh, dissolving, and increasing for gases will decrease. Gases will want to bubble away, and the more energy you give them, the more they're going to want to bubble away. All right, so let's talk about how to read these things now. So the way you read these things would be how many grams of potassium nitrate can be dissolved at 45 degrees in 100 grams of water. So here's our temperature. So 45 degrees is going to be here. Would you agree? This is 45 degrees right here. 45. All right. So we're going to go up to, I believe it was potassium nitrate. So we follow this line up to potassium nitrate right here. The question was how many grams would go in? So that means we're up here that about 90, right? Would you agree that we're going to end up here? So this dot here is at the 90 grams per 100 grams of water. So potassium nitrate, KNO3 is this line, and it goes up to, at 45 degrees, which was the temperature we were at, 45 degrees right here. So that would dissolve about 90 grams of potassium nitrate for every 100 grams of water. And that's what we got to do for these kind of problems. So let's look at the next one. What solid has a solubility that is least affected by temperature? So let's take a look here. Which of these four solids is least affected by temperature? So as you increase the temperature, the solubility doesn't really change. If you take a minute to think about that, this is increasing, the potassium nitrate, the KBr is increasing, but the sodium chloride is really not increasing much with temperature. So that answer would be NaCl is the solid that does not really seem to be affected much by temperature. All right, so you can try to do the rest of these from the packet on your own. So now let's talk about ways to increase solubility of solids. If you want to increase the solubility of your solid, here's some things you can do. You can agitate it, and you know this. You mix when you have sugar in water or salt in water. If you mix it up, if you stir the solution, if you agitate the solution, it's going to help break up that solid. It's going to give some energy to the water. It's going to help break that solid up, and it will distribute the solid into the solution. So agitation is one way. Crushing, if you make the pieces smaller, and I hope you have some experience cooking and whatnot doing this. If you make the pieces smaller, the solid has a greater surface area and it's easier to dissolve. There's more access for the solvent to pull it apart. So crushing will also help you dissolve a solid. And temperature, increasing or decreasing. There are some solids that actually do better at decreased temperature. And you might see some of those on a chart, but you'd have to have this chart to know any of that. So typically solids, as you see here, increase solubility, but basically playing the game, whatever it is, temperature-wise, if you got to increase or decrease the temperature to get more of it to go in, that'll help increase the solubility. All right, so getting back to our molarity equation. So we talked